Okay, so now it's time to change notation. What you're going to engage in Chapter 3 is really, in many ways, the heart of what we refer to as differential calculus. Everything you guys have done up to this point is really the background. As a matter of fact, in ancient times, they knew how to do a lot of differential calculus. However, what? Oh, however, they did not know how to express it properly. In fact, the theory of limits was what was developed much later, which is kind of what we studied. So um, I want you guys to just think, though, for a second. Take that, Ella Otten. Yes, exactly, exactly. It won't take much to find out who it is because I will see the number and I have all those link leader emails written down. So okay. Or maybe you texted Colleen already and told Colleen to send more my way. Anyway, so with that said, differential calculus, really the ideas begin to take shape here. And but okay, so where I was at, I want you to just think for a second how much new material you've learned so far. Entering this course, you did not know how to find instantaneous slope. Entering this course, you did not know how to find a limit. You did not know how to prove it. A lot of those pieces are entirely new, and we'll continue down that route. Everything that you learn will be very new. This test, 3-1 through 3-3, was difficult for a lot of students, and I anticipated it to be the easiest one. And so knowing that now, I think it will be a very easy test. However, for whatever reason last year, it was tough. So funny thing is, this one involved a lot of algebra. So I just figured that should be good. So hopefully your algebra skills are up to par. Derivative. Definition derivative. A derivative is something that is based on another source. So in terms of x and y, here's how we say what the derivative is. The change in y based on the change in x. The change in y based on the change in x. Now, what is that? Does that sound familiar to anybody? Does that kind of slope? Yeah, it really sounds like slope. In fact, we would say slope would be represented, we've said y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And that's really the change in the y values, right? Well, the notation for change that is used within the Greek language is a delta, and it's a capital delta. So you saw the lowercase delta, that's the uppercase delta. So delta y over delta x. Now, those are synonymous with slope, but derivative is different. The derivative is really when we take the derivative of something, we are operating on it, kind of like when you take the sine of something. And the way that we imply derivative, there's many, many, many notations, and you do need to be aware of all of them. One would be this, f prime of x. So f of x would be the original function, f prime of x would be the derivative. We may say y prime. Those are synonymous. We may say the derivative of y with respect to x, instead of a change over a given interval instantaneously at one point. You may see this defined as the derivative of the function, whatever name it might be, with respect to x. Other notation. The derivative with respect to x of the function. And finally, the derivative of the function. So these are all terms that are used very commonly. I will say that These are the three that are used most often. So we already know this. We are now going to define it. So this is getting some notation all the way. I haven't said derivative before, have I? Have I? Okay. Well, derivative, before I've just talked about instantaneous rate of change. And that really does represent the derivative. Namely, the derivative of a function f at a number a can be denoted by simply this formula, which we are all very used to seeing. Let me make sure that the book gives you the exact same notation that I do. And yes, they do. The limit as h approaches 0 of f of a plus h minus f of a all over h. Hold on. That is now equal to, before I wrote slope, right? We're now going to call that f prime of a, the derivative of the function at a. The derivative of the function at point A. Now, I'm going to write one more part here so that we kind of connect everything that we've learned. The slope of the what? The slope of the what? The slope of the tangent line at point A. Now again, I wasn't so impressed with your work ethic during the first test. Your second test, I was more impressed with your work ethic, but I was also impressed with your patience. You've understood that sometimes it's going to take a couple days to wrap our brains around this. Some of you guys will get this right away. Some of you guys will struggle for a few days. Let's just, this is really a basic example, but it's also somewhat difficult for people to understand. It says for the function f of x, we'll call this f of x. It says arrange the values in increasing order. F prime of negative 4, F prime of negative 3, F prime of negative 1, F prime of 1, and F prime of 3. So, can you make sense of what that's actually asking me to do? What's it? The slopes at those points. So I first want to find negative 4, which would be, let's see, 1, 2, 3, 4. And would you agree that that's approximately, the tangent line that would be represented at that point? Would you agree that that's a pretty negative slope? All right, let's just draw the lines first, and then let's arrange them in increasing order. F prime of negative 3. What do you think the slope of that is? Looks like 0 to me, right? In fact, it looks like it bottoms out. And anytime a function bottoms out, or maxes out, generally speaking, there's going to be a tangent line with a slope of 0 there. That's something we get to later on. F prime of negative 1. What do you think about that spot? Tell me something about the slope. Give me an estimate or anything. Okay, it's positive. 1, maybe 2. Okay. How about F prime of 1? Looks like the exact opposite, so maybe a negative 1. And then F prime of 3. Okay. So I guess you could try attaching some values onto these if you want. Maybe this first one you would say is maybe a slope of like negative 5. Maybe the second one is a slope of 0. I think that would be pretty accurate. Ben, you suggested maybe a slope of 1. Kyle said maybe negative 1. And somebody you said, maybe this says, I don't know, we'll say pretty positive slope of maybe 4 or something like that. Now, am I exact in the numbers I chose? No, I'm just giving a reasonable estimate so I can arrange them in increasing order, okay? So, what would be the lowest one? F prime of negative 4 is less than F prime of 1 is less than f prime of negative 3 is less than f prime of negative 1 is less than f prime of 3. So there we have it. Notice that this is different than f of negative 4. F of 1. Those would actually be the height or position value, the coordinates of the function. Everybody see that there's a distinct difference between these two. When you see this, you think immediately, slope of the tangent line. Any questions on that one example? We're all good? Okay. All right, we move on. Okay. This is a question that would confuse a lot of people. Okay, so first thing is you got to understand why you would find it confusing, and second of all, you got to understand how to figure it out. It says if the tangent line to y equals f of x, are we actually given a rule for the function? No, we're not. To y equals f of x at negative 2, 3 passes through the point 1, 9. I need to find f of negative 2. I need to find f prime of negative 2. Any thoughts at all? Okay, find the slope. Subtract. Okay. We do have one of the answers already, Isabel. Same thing. Okay, so let's do this. Let's sketch just a quick little graph. And just, we don't know what the function looks like. But we do know that the line passes through point 1 and point 2. Would you agree? Okay, so I'm going to sketch those points. I'm going to make each one of these 5. Okay, so 10, 10. So negative 2, positive 3 is going to be somewhere right about there. And 1, 9 is going to be somewhere right about there. So, can everybody, first of all, agree that that represents the line tangent? Where is it tangent at? Negative 2, 3. So I don't care how you want to draw your function. It doesn't really matter so long as that, you know, it touches tangent at that spot. Okay? And that's just to try to give us a visual. All right? So let's look at what this question is actually asking. Find f of negative 2. That means if I plug in negative 2, I have an output of the function. What's the output of the function at negative 2? 3. Yeah. F of negative 2 is equal to 3. But now it wants to find f prime of negative 2. That's just my function. I just drew a arbitrary function that has absolutely no really connection other than we just see it touches tangent. But f prime of negative 2, f prime of negative 2 represents the slope of the tangent line at that one point. Can I find the slope of that line? Yeah, very easy. What do? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I get 6 over 3, which is 2. Is that clear? That's it for that problem. But do you understand where we're pulling those values from? The difference is that you have f of negative 2 and f prime of negative 2. You need to understand that distinct difference. Okay. Number 3, I would like you to try to see if you could think through this on your own. I'm going to give you about 2 or 3 minutes. You could talk with a partner. It says sketch a graph. Now I want you to know there's an infinite number of possible graphs. where f of 0 is 4. So the function defined at 0 is 4. F prime of 0 is 1. F of 1 is 0. And f prime of 2 is negative 3. You just see if you can come up with any parts of those. Talk through it with your partner. I want you to investigate it first, and then we'll go through it together. Take 2 minutes, talk, see what you can come up with. Go. Okay, here you go. Let's just start with the basics. We first need position, okay? And this represents position. We know an actual placement of the function. We know position here. Here we're looking for slope, and here we're looking for slope. Right? So let's get those requirements out of the way first in terms of actual position. So what coordinate do I have right here? 0, 4. So I'm going to mark 0 and 1, 2, 3, 4. I'm going to put a dot. So that one's taken care of, right? I'm going to now take care of my other position. And just because I see how this works out a little bit, I'm going to give myself a little bit of space. How you doing, sir? Good to see you. Okay. We'll get our second requirement out of the way. So those two must be the same on everybody's graph. How we accomplish these next pieces is entirely up to you. Now, all I'm going to do is make sure that my curve passes through this spot and it passes through this spot. But I also need to make sure that I have a very distinct slope. What's the slope supposed to be right here? So I'm just going to draw a short line that has a slope approximately of 1. What do you think? Is that okay? Okay. And then at 2, I have a slope of negative 3. Now, do I have to be at a certain spot on the graph when I draw this? It doesn't say that I have to be anywhere in particular. So I'm going to, just for the sake of doing something different, I'm going to draw it above the x-axis. I have a pretty strong slope going down. So that's all I have to do. I just have to pass through here. Doesn't matter really where you start it, just as long as I have a slope of 1 passing through there. I have to pass through this point. I'm going to touch down and go like that. And then I have to have a slope of negative 3 at this spot. And I would say that's pretty close to slope of negative 3. So there's an example. Here's another example. This is what I drew on Tyler's paper. I again had 1, I had 2, I had 3. So I passed through here and I said I'm going to have a slope of negative 3 that goes like that. And so I passed through there and then I kind of picked up that spot of the graph. There's another example. Does somebody have one that they want to put up here that they think might be right but is different? Mark? Very good. Mark does not have a continuous function. That's not part of the requirement. As I said, there's an infinite number of ways to accomplish this. In fact, he could draw a very disjointed function that would pass through there. He could even cap it off there and then pick up something down here. You can do all sorts of things like that. So works out just fine. Okay. All right. Let's do one more example, then we'll pick up the rest tomorrow. No. I feel famous because I know you, Ina. I just always reference your Sundrop commercial, and then I feel famous. All right. Given the function f of x equals 1 minus x to the third, find the equation for the line tangent at 1, 0. So if you hear something where you have to find an equation for a line, we need to come up with two pieces. What do we need to come up with? Slope and a point on the line. The point on the line is 1, 0. And we know this, that slope is the same thing as the derivative of the function at that point A, which is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So that's going to be the slope of that tangent line, which is the same as the derivative at that point. Does everybody understand that notation? Okay, now we go to work. This is the part that you guys all know how to do, right? Help me set this up. What do I have? The limit as h approaches 0 of what? One minus, parentheses, to the third, good. Minus 0 all over h. Well, I have my function, which is 1 minus x to the third. I plug in 1 plus h for x. So 1 plus h for x. Then I subtract off oh, no. So now we expand. 1 minus parentheses. Using our binomial theorem of expansion the other day, what will 1 plus h cubed be? H cubed? Good. Rebecca and Jalen kind of had those pieces in there. Good job. You can see that we have some cancellation between the ones. F of a is 0. So those cancel. I'm left with the limit as h approaches 0 of, negative h to the third minus 3h squared minus 3h all over h. Divide off the h. The limit as h approaches 0 of negative h squared minus 3h minus 3. Can I now plug in 0? What do you get? So that's my slope. I can now use y equals mx plus b. Y is 0. M is negative 3. X is 1. 3 is equal to b. Y equals negative 3x plus 3. That's the equation for the line tangent. Okay. I'm going to give you guys some time to work on some assignments tomorrow, but this is where we end for today. How is it different? It's not going to be a lot different, but it's going to change in the next 2 lessons.